So, hi everyone, my name is EOP Chen. I'm a compiler engineer from Sci5. Today we're going to talk about how to add C intrinsics and code it, using the RISC-V vector C intrinsics as an example. So here are some background checks. How many of you are backend developers? And how many of you has ever expanded ISI instructions inside the compiler? Cool. Well, today's tutorial won't be for you guys because we're going to answer that question today. Today's tutorial would be an end-to-end walkthrough of exposing an instruction with intrinsics in the C language. So here are what we're going to cover today. This talk is intended to be a tutorial. After all, in my opinion, in about 90% of the time, we are the API users of the LLVM. And the goal of this talk is to first give audiences an overview of the infrastructures in LLVM for intrinsic developments, and also give audiences an understanding of how the RISC-V intrinsics are developed inside the compiler. And after we have covered all the code base we have in the RISC-V backend, we will demo using how to add a new instruction and expose it in the C language for the RISC-V backend. And in this talk, we will be going deep into the code base, so be prepared to see multiple snippets in this talk. So let's start the story from what are intrinsics. Well, users seek for better performance. So in benchmark and high performance libraries, hot kernels are investigated thoroughly, and a slight difference in the loop may impact the performance. Well, aspects that may affect performance are like instruction counts, register allocation results, how the cache performs due to instruction execution sequence from scheduling. Well, upon identifying those regressions or potential improvements, we have two possible ways to resolve the problem. The first one is source code tuning, which requires us to directly change the written source code so the compiler will perform differently. The other one is to improve the compiler itself and let it generate better code without modifying anything from the source. Well, of course, the first approach is obviously the more straightforward approach and should be considered to be more effective in the short term. Well, since we're targeting some ideal code sequence that we figured out, this brings us to the inline assembly. Well, using the inline assembly allows programmers to let the compiler emit the exact assembly desired in the C language. In other words, you can have your own register allocation, your own scheduling, or your custom calling conventions that allows you to speculate and achieve higher performance. Well, however, handling these tasks on your own may be troublesome. Well, if you're writing inline assembly, users may fail to clobber memory, or they would fail to recognize an early clobber of a register. And since you're coding at a low-level semantic here, the compiler cannot help much on analysis, and it's hard to debug. And on the other hand, this may be a tailored code sequence. So, well, the performance aren't guaranteed across platforms. By platforms, I mean, well, if you're running on a different CPU, then you're expecting a different cost model. So this brings us to the intrinsics. Given that the inline assembly gives users absolute control, but it is hard to maintain, we have the compiler expose interfaces with a similar level of control, but let the compiler deal with the tedious tasks, which may be register allocation or instruction scheduling. So here is a general workflow in LLVM. We start from the C language, take it into Cheng and transform to LLVM IR. Then the IR is scalarized into a DAG for instruction selection and type legalization. Then it is turned into a machine instruction for backend code generation. In this talk, we will go step by step through the infrastructures for intrinsics in the compiler. This would give you a feeling of what you will need to cover when creating a new backend and exposing them in the C level. Well, we just talked about intrinsics being the interface to low-level semantics in a higher-level programming language. So what we're going to do here is pretty straightforward to have them inside the C language. We also add interfaces in the LLVM that contains the low-level information we need. So this would be the overall workflow. And let's look at them one by one. So starting from the C intrinsics, we will be needing to declare types for the intrinsics. And since we're extending a new instruction here, and we may be exposing control to something non-scalar, which we're taking example is the vector architecture. So we will be adding new types in the compiler. In the compiler, you can see that this built-in class here are the base class in Cheng that records the type predefined in the compiler. Well, you can see blanks inside the snippets, and these snippets will be filled with while we're going through the RISC-V backend. And also, we would need to register these types when we're initializing for the abstract syntax tree. You can see on the snippets, there are other built-in types in the compiler which we use daily. The void types, the char, the int, the long types. They are also initialized here. So recall that we're talking about intrinsics from C. Well, the front end is responsible for taking them into the Cheng front end. Then we need to turn them into LLVM. This happens, the whole process happens under Cheng/lib/codegen. Specifically, we're talking about built-in types here. So this particular function is responsible for turning them into LLVM. You will need to handle the type conversion here. Now for the built-in functions. We start from looking at how other built-ins are declared in the compiler. There's a .dev file here that will be expanded to declarations under built-in.cpp. For the mysterious second parameter of the macro, they are the prototypes of the built-in. They map to the prototype listed here. In the slides, we show the encoding of those prototypes, and on the right side are the expanded prototypes of these built-ins. And also, we are a compiler that will provide semantic checks too. Semantic checks for declaration, so for built-in function calls are under check target specific built-in function call. Also the same for custom built-in types. Semantic check for declarations are handled under sema declaration.cpp. Now, for extending intrinsics in the LLVM. The intrinsics are declared with TableGen files. They start from the intrinsic base class. The value types here are LLVM value types. And what you will need to be looking at what you will need to focus on would be the return types and the parameter types. And since we will be using a vector extension as an example, you may imagine that the IR value type here will be the scalable vector type. And since we have covered for the built-in functions and the built-in types and the LLVM that will be lowered in the next level, here is where the transformation actually happens under cg built-in.cpp. The input values are collected here, and the IR builders are called to create functions to the intrinsics that was just defined. For the backend and machine instruction mcinst part, well, I think the talk Alex Bradbury gave in 2018 gave a detailed explanation of it. So I don't want to repeat the contents here. Well, what was detailedly covered was how to describe an instruction, the selection pattern, the selection process, and how basic pattern matching in TableGen works. I think the high-level understanding we need today here is that the LLVM during instruction selection, the LLVM is turned into a DAG, and high-level semantics are lowered one level lower to closer to machine code generation. Type expressed in high levels that are not available in the machine will be legalized in this phase. Make sure I don't play the video. Well, now, after we have gone through the basic workflow inside LLVM, let's look at the case study today, which is the RISC-V vector extension and its intrinsics. I will be abbreviating RISC-V vectors with RVV for the rest of the talk to make it easier for us. Well, I think the fastest way for you to get a feel for RVV is this code snippet. This is a strip mining loop that does addition and shift. You all can see my cursor here? That is doing a addition and shift for a element width of bit width of 16th. And on the second segment would be a shift, add, and sub for a source of element of bit width of 32. And the terminal condition here would be where we run out of elements. Well, what is special for RISC-V is that how many elements the vector instruction will be processing in that loop iteration is depending on the configuration set into the CSR. The setting of the configuration is done by the vsetvo instruction here, which is highlighted in the red block. So you can see that between the instructions, we do not contain status of the configuration. Well, the vsetvo configures the element width and the register grouping parameters that controls how many registers is associated in the vector instruction. You can see in the illustration that for M4, we will be controlling 4 vector registers in a single vector instruction, and for M8, we will be controlling 8 vector registers per vector instruction. So you can see if we're trying to expose this kind of semantic in the C language, for a vector instruction, we will have different kind of variants that contains the execution status we desire for the instruction execution. And for more illustration, I think we can have an implementation here for reduce max. Well, on the right side would be the scalar implementation of finding the maximum elements inside a vector. And on the left side would be the RISC-V vector implementation. Well, in iterations, we will be processing upon the maximum element we can find inside a single vector register, assuming it to be four elements. It will be going. And the vsetvo would be to determine how many elements we will be processing in the iteration. So in the third iteration here, the VL would be 2. And after the loop, we will be using the reduce max instruction to flatten the elements into the first element of the vector register and to move it out as the return value. So you get the feeling of vector executions here. Now, coming back to the vsetvo instruction, this is another tedious task like register allocation and instruction scheduling, where we hope the users do not need to worry about. So we don't want to expose them inside the C intrinsics. To achieve this, we hold the status desired until the backend, where we strip it out and insert vsetvo instructions in between them. You see that in the illustration, we have the C intrinsics and the LVMIR corresponding to it, and the single instruction, the single vector addition instruction in LVMIR here actually maps to 2 instructions inside the code generation, which the first instruction would be the vsetvo to configure how many vector elements we will be processing and what are the element width and what is the register grouping control parameter. And an additional note to this is that having how many vector register we need to control is also some information we need inside register allocation. So this would be another reason we want to keep them in the LVMIR. So having the status being preserved is not exactly what we will be emitting into the machine instruction, into the machine. So in the RISC-V backend, we have the pseudo instruction layer that will be containing those instructions to deal with vsetvo instruction and register allocation. Then those pseudo instructions will then be mapped to MC instructions afterwards. Now, given the workflow, let's fill in the blanks for the RISC-V backend to the code base we have covered in the previous section. Starting from the C intrinsic parts, we will be expanding custom types for the vectors. Well, a strongly typed scheme will have the intrinsics express the info we need to do the vsetVO configuration. The types are defined under RISC-V types.def. The first parameter apparently are the built-in type names. The second parameter are for enum kind inside built-in type. And the third type will be used as the singleton type initialized inside the abstract syntax tree. The rest of the parameters are info of element width, register grouping, whether it is a tuple or whether it is a floating point type. Now, for converting the types to LLVM we handle them inside the built-in vector type info structure, which is a shared interface with ARM SVE. In the function, we parse the built-in types to contain info of its scatter type, the vector element count, and the rows of vectors that the type contains. Well, illustrations here show how the vector info is turned to scalable vector types. These v-scales are unknown during compile time and is a constant during runtime. This is the vector length agnostic feature for vector architectures like SVE or RVV, to be able to have binary executables upon a scalable vector register length. For defining built-in functions, the initial approach for RVV also resembles what we have introduced in the previous section. The first approach lists out all the variations and declares them in the macro. However, there are so many variations we would be generating through scripts. So the current approach improves from that, and we have a RISC-V underscore vector.td. The TableGen file will then be leveraged by the RISC-V emitter, which enumerates through the element width and the register grouping for the intrinsics. Semantic checks here handle whether if the intrinsics is supported by the architecture. Also, the compiler also checks for parameters that are required to be constant here. Well, if you actually look into the code base, like inside the whole file, you will actually find a decent amount of boilerplates inside the code. Well, the constraints for built-in function calls are customly handled under this function with like a giant switch case. And we actually do not have an elegant way to specify the constraints and allow more automation and boilerplate reduction here. And so since today this is a tutorial, I think this is a good starter task, or for anyone out there to see if we can expose some hooks in the definition file of the intrinsics and that the constraints be handled more gracefully here. And this improvement doesn't specifically belong to RISC-V. You can see that for x86 intrinsics, they suffer the same problems too. Also, variable declarations are needed to be guarded, just like we have checked if the intrinsics are available. As you can see, like for examples, a value type of 64 bits would only be available when an architecture of 64-bit is specified. Recall that we have just mentioned that the RVV intrinsics has an overwhelming amount of intrinsic variations. We even have other configs we hope to control, and it turned out that for a single vector instruction, we have almost 200 variations. Well, an overwhelming amount of variants also happen to OpenMP and ARM, and we need to deal with them in RISC-V as well. Well, here was the initial approach that I've mentioned. A single intrinsic interface maps to its built-in function. Then, to reduce the number of built-ins, we have the interfaces to alias to the same built-in function in the compiler. However, we still get too much interfaces. And this leads to a larger Clang binary and requires more runtime memory during compilation. Also, if we're trying to build the mapping of intrinsics all during the compile time during Clang, the build time of Clang will actually grow too long. The current approach gives us speed up by balancing what we do during building Clang and the actual compilation to the source code. Here you can see that the lookup table is pre-built during the compilation of Clang. Well, this code here is actually the trigger of the lookup during compilation of the source code. Well, this picture would be what the lookup table actually looks like. The lookup table consists of intrinsic names, its prototypes that will be added into the symbol table during compilation. And this table was built during Clang. And during the compilation of the source code, the compiler lazily constructs the built-in function table at the first symbol lookup of the RISC-V intrinsics based on the pre-built lookup table. So here, the index 957 would correspond to three parameters of the prototype, and the prototypes would actually resolve to 3 identical vector types, which will be filled inside the signature. Now for the parts in the LLVM IR. Recall the base class of the intrinsics under TableGen file intrinsics.td. In RISC-V, the declaration of the intrinsics are through layers of templates. At the very bottom of the template, the intrinsics can be overloaded that allows any vector types to be the return type. Then the parameter follows. The third parameter may be any type, since for an vector instruction, we can take either 2 vector registers or 1 vector register, 1 scalar register. Well, you may see a direct mapping in the illustration on the right with the types highlighted. And you may see through the lines that this is a bottom-up matter of template reuse, which the actual instruction name is derived, is declared at the last level of the template. For convergence from the Clang frontend to the LLVM IR, basically under CG built-in, we have a large switch to handle the creation of the intrinsic calls in LLVM IR. This switch is auto-generated through scripts through the RISC-V emitter that also consumes the definitions in RISC-V_vector.td. Now for the pseudo instruction layers. The pseudo instruction layer is something we have extra in RISC-V, like I've just mentioned, to deal with the vsetVO instructions and register allocation. The structure pseudo info is used for lookup between the pseudo instruction and its MC instruction. Well, it took me some time to look around and trace, so I think it's a good material for people that I actually pointed out where the actual conversions happen. Well, where the actual mapping happens. As you can see on the right, the class RISC-V pseudo is using the pseudo instructions as a key for the table, searching for the base instructions. Then, under where we actually declare the pseudo instructions, we have that class being appended to allow it to be added into the table for lookup. You will find code for the pseudo instructions to be rewritten to MC instructions under RISC-V ASM printer.cpp, where the mapping actually happens here. This is where we strip off the traditional, the trailing additional informations, the VL, the SCW, the policy, and the rounding modes possibly for floating point instructions, and turn them into MC instructions. From the pseudo instruction declared, we have derived multiple layers of templates, since for the same instruction, we have masked and unmasked versions. And for them, we will have versions of different operand mnemonics, which take 2 vector registers or 1 vector, 1 scalar. And this brings us to another level of template. And you can see with the same manner as the RISC-V, as the built-in declarations, the actual pseudo instruction declaration is shown here. Pattern matching from the LLVM IR to the pseudo instructions are also declared in the same file. On the right side, you can see the LLVM IR and the corresponding pseudo instruction that will be replacing it in the selection DAG. Now for the part where we describe the instructions. This illustration shows where we describe the vector instructions under RISC-V instruction info V and RISC-V instruction format V. The encodings comes from the specifications of the instruction set architecture. Now, for the last section of this talk, we will go through a short demo of how to extend an instruction for the new bflow 16 extension. So you now have a new extension. You want to take bflow 16 as an input, as value types, and to do maybe multiply adds or conversions into floating point formats for them. Well, this will become easy once we have pointed out all the points of modifications you will need during the previous section. So what we will be doing, when you're extending a new instruction, you will be doing that in a bottom-up manner, because you won't be receiving the requirements from the C interface, because you're having a new instruction. So you're going to build the assembler first, then we'll stack them up to the C intrinsics. So for the machine instruction, this simple snippet would be how you add a new machine instruction that encodes. That encoding is provided by the extension. So what we're using an example would be a widening convert that widens a bflow 16 to a float 32. Then we go up to the pseudo instructions. We already have widening converts for the standard vectoring extension, so the templates can be directly reused, so the modifications would be simple here. And for the LLVM intrinsics, also we have existing templates, just directly reused RISC-V conversion. And for C intrinsics, you'll first need to declare the bflow 16 types, and to have the actual built-in function declared. Well, there are also other details which you will need to add encoding, because we are introducing a new type here, so you will need to be adjusting the parsing of the encodings inside RISC-V emitter, but it'll be quite complicated to go through that here, so I won't cover that today. But you get the feeling that to extend a new instruction inside a RISC-V backend would be relatively easy. And that is all for today's tutorial. Here are some learning resources. And thank you all for today's attention.
We have plenty of time for questions.
Thank you very much. That's very useful. I have a confession to make at the risk of being lynched here, is I have done intrinsics before, but for GCC. and not for LLVM. So this is for me to understand how you do it in LLVM. Am I right in thinking the intrinsics you're describing are all a one-to-one mapping from the intrinsic to a single vector instruction?
Yes, because you want the low-level semantics inside the C language, right? So what you will be doing inside a vector instruction, I think it'll be kind of plainly mapped into the intrinsic function interface.
Okay. So when you have intrinsic functions that may map to low-level semantics, but not necessarily a single instruction, you presumably need more there. And I'll give you an example, which is from one of the ETH Zurich RISC-V extensions, where you've got an arithmetic operation which comes in two flavors, one where you set the second argument in a register, and one where it's a constant integer. Now, when I do a built-in or an intrinsic, they're not exactly C functions. They're strictly speaking outside the standard. That second argument clearly has got to be an integer. But if it's actually given to me as a constant, I can use the constant version of the instruction. If it's given to me as a variable, I've got to load it into a register because I don't know what the value is. So I've got two possible instructions I could generate. I've got the low-level semantics. It's quite clear from the C. It's a perfectly valid way of doing it, and it keeps my number of... But how would I go about doing that within the LLVM framework? So I had alternative low-level semantics.
Well, the LLVM compiler actually also does this optimization inside of LLVM. Like we also have for the vector instruction, you may have Vx, which the x would stand for a scalar register, or Vi, which the I would be an immediate. So there are two different instructions you may be emitting. And in the compiler, we're exposing only the Vx interface here and relying on the compiler to recognize this is an immediate and call the write instructions. And I think this happens inside selection DAG. So
okay, so it's inside selection DAG that I would make this. Okay, thank you.
Yep.
Hi. So my question is, so previously, all the signatures for the RISC-V vector intrinsics were generated in the RISC-V vector.h file, right? And in order to reduce the size of that file, now they are being table-genned, and the signatures are determined on the fly by...
Yes.
So previously, if a user of the intrinsics referred to that header file to know about how to invoke them and what their signatures and the parameters are, how does the user now use them? Because now the signatures are not readily available.
Yes, that's a good question, because there is a public specification inside. There is a GitHub repo that gathers the intrinsic prototypes. So I'll point you to the GitHub repository. Like users should be, the intrinsics should be a specification that is implementable for both GCC and LVM. And this is not a place where we don't have a place that in LVM to point the users to, but we have a common place in the RISC-V community to point users to know what intrinsics they will be calling.
And is that resource updated regularly?
Yes, it's a public repo.
Okay. And my second question is there any difference between the term intrinsic and built-ins, or can they be used interchangeably?
Yeah, I think it's two same synonyms.
Okay, thank you.
Hi.
Hi.
Just a quick question. Can you specialize intrinsics based on the return data type?
Sorry, the current...
Sorry? The return data type.
May you repeat again?
Can you specialize the intrinsics based on return data type, and does the whole Clang table gen approach now to generate intrinsics support that? For example, let's say I have a vector read instruction from memory location. I can just give the memory location, but the destination register can be different. It can be a V8.
I think this for you to actually implement that requirement, you will need to figure out how you express them inside the LVMIR. And starting from that, you expose interfaces in the C language, and you handle them inside the cogen part, where we bring in we recognize the type and have a LVMIR value type to take them into, and that's where you bring them to the backend to do your backend work.
Do you know if there is an existing example on that, on something like that in Clang or?
Yeah, I think we have covered that inside example where, let me just point it out. Where we are declaring new types here. We are declaring new types here, right? And then this will be where the conversions happen. The conversions where you turn them into LLVM IR. And if you're trying to do like custom calling conventions, I think it's siege cogen function or like CG statement, where under the same directory of Clang lib cogen, where you can have your own calling convention of lowering them to the LLVM IR.
Mm-hmm. Okay, thanks.
Yeah, so check out the directory, or you can ask me more offline.
Thank you.
I actually have a follow-up to that same question. And if I can restate the question is, can we specialize the intrinsics based on just the return types and not the argument types?
I think that's a limitation inside the C language.
Yeah.
You can't do that.
But at the intrinsic level, there is something called as overloaded return. Do you know how to use that, and if that is meant to solve this particular issue?
I think I'm not familiar with the attribute, so I'll look into it.
Maybe we can talk offline.
Yeah.
Thank you.
I have a question out of curiosity. So in your experience, having gone through the exercise from the front end to the middle end to the back end and knowing what it takes to add a new intrinsic, is there something fundamental to LLVM architecture you would think it would be good to change? Or do you think that is fundamentally has a headroom for improvement?
Well, again, I think we are API users for TableGen, so in my opinion, extending the intrinsics hasn't shown like great fiction, except I mentioned the customized checks for it inside the semantic checks. So to me, I think it's pretty convenient, and probably no.
Thank you. And one question, as a second question, it's mostly unrelated, but out of curiosity, how far do you think we could go in automating some of this, say, just in terms of adding support for new instructions to the backend, making use of formal semantics for instructions? Like, I know there is work done by ARM for machine-readable formal semantics of instruction set architecture, as well as some work and academic work for like SAIL for RISC-V instructions, expressing the instruction semantics. Is there some path to someday having automated support for that in generating the support in the backend?
Well, I think the question, to repeat your question again, I think you're talking about like for us to define something useful to
yes.
like for a YAML file that will be directly parsed into TableGens like this.
Yeah.
Well, yeah, if you're willing to have a script to auto parse this into this TableGen file, then it would be good. But you will still need to be declaring those actual instruction formats inside the LLVM to have the TableGen work. So if that is the case, I think it won't be that more helpful to have another layer of abstraction. Yeah.
All right, makes sense. Thank you.
No problem.
Hey.
I'm curious, how many files do you need to touch to do one intrinsic like this one?
So you'll need to split your implementation between front end and back end. So regarding intrinsics, you will be speaking about that you already have them inside the assembler. So what you need is have them inside the LLVM IR. You will be exposing a intrinsic function inside the LLVM IR that the intrinsic built-in function will lower into. And so regarding that, I think the backend work was already done since you already have the instructions ready. So I think the work will start from the first two blocks of what I've covered, which is the LLVM intrinsics and the C intrinsics. Yeah. Nope. Two main parts, but like 6 or 7 files. Yeah, across.
Thanks. I'm kind of curious to get a feel.
Yeah.
I had a question regarding the backend flow, right? After the selection
Sure.
tag, you have this pseudo instruction phase. Why do you need that part?
Yes, because in the RISC-V backend, we mentioned the VSET-VO instruction that we have to model. Let me just. This VSET-VO instruction, because this is like a you can consider this as a global value, which the results of the vector instruction execution depends on. So we need to obtain we need to gather that information for emission of the VSET-VO instruction and also for register allocation. So what we did was we have this pseudo instruction layer, but I think it's not that different from machine instructions, but it's just for us a hack to directly transfer this pseudo instruction to MC instructions in the ASM printer.
And you do your register allocation while you are in this
Pseudo instruction phase.
Okay, intermediates. Okay.
Anyone else? Well, that was a really, really clear walkthrough of the steps involved in adding intrinsics and lowering them in a target-specific manner. Thanks to you, Kito, and the entire team. And thanks also to the audience for keen attention. And I'm happy to see lots of questions coming from this. We'll now take a break. And I believe the next session is sponsors meet and greet. And we'll be back here at 3:45, I believe. Sorry, at 4:15. Thanks, everyone.